Okay, we are back, and what I'd like to do now is take a look um, at the problems in section 2.2. Sorry, I'm still. Let's see how to make this stuff go away. There we go. Excellent. I'd like to look at the problems in 2.2, which had us doing induction proofs. Now, if you remember how these go, we prove the formula for the lowest number integer that we're going to deal with. And then we prove that we assume it holds for k and show that if it holds for k, it'd have to hold for the k plus 1 case. Then what we can do once we have that is we go back to the first case, that gives us the second gives us the third, and so on and so on and so on. So that's the idea behind an induction proof. Let's actually work through a few problems. And what I'd like to do in this first section is just work through problem 2, which had 7 problems on it. But I think that'll be a good start for us, and then we'll pick up after that. So if I were going to prove this using induction, the lowest number that this should hold for is n equal to 1. So that would be my first, my base case here. I would look at this formula and say something to the effect, note that 1 squared is 1. And then look at this formula with n equal to 1. So this is 1 times 1 plus 1 plus 2 plus 1 over 6. So this is 1 times 2 times 3, which is 6 over 6, and that is 1. So the basis or initial step holds. Now what we want to do is assume that it works for k. So now assume that when we add up from 1 to k all the squares, that gives us k times k plus 1, 2k plus 1, all over 6. And let's consider the sum as I goes to 1 to k plus 1 of the I squares. And then let's look and see. Now what we're going to do is we're going to peel out that last term, that k plus 1 term, and use what we know about the first k terms to help figure this out. So when we're looking at this sum, I going 1 to k plus 1 of the I squares, really what we're going to do is look at the first k terms and then pull out that, if I were k plus 1, we would square that. Okay. Then based on our assumption, this part right here is k times k plus 1 times 2k plus 1 over 6, and then we've got k plus 1 squared. Now, it's a good question to ask yourself, what do we want this to look like when we're done? Well, think about this formula right here with k plus 1 plugged into it. Now, we can't say it's equal to that, but that's what we're shooting for. So we'd have a k plus 1, and then a k plus 1 plus 1, that's k plus 2, and then 2 times k plus 1, so 2k plus 2 plus 1, so plus 3, and then the 6 would be what it is. Alright, so that's kind of our goal, but we can't say it's equal to that. We have to show that it's equal to that. Alright, Now, if I were going to try to clean this up a little bit, I would get my common factor of k plus 1 out of there. Okay. And that would leave me then with k times the 2k plus 1 over 6. And then it would leave me with another k plus 1 right there. So, and I like having that 6. You know, my answer is going to have a 6 as the denominator, so it makes sense to me to try to get a common denominator if we can. So here's k plus 1, and then inside of here we put all this over 6. So this is 2k squared plus k, and then we'd have to say 6 times all of this stuff. So plus 6k plus 6. So 2k squared plus 7k plus 6 over 6. And I'm hoping here, let's see, yeah, this middle term, I think if we did 2 times 2 and then 1 times 3, right? So k plus 1, leave that alone. And then here, 2k and k, and then I think they want this to be a 2. They're both going to be pluses. And then a 3 here, so that's 4k, and yeah, good. Over 6. And that gives us then, this actually kind of matches up to what we found. This is the k plus 1, k plus 2, and then the 2k plus 3 over 6. So it actually gives us the formula for k plus 1. Great. Thus, the inductive step holds. Therefore, by induction, the formula holds for all n in the natural numbers. Okay? And we did. Okay? See if that makes sense to you, what we're talking about there. It forces us to do a little algebra, but we should be okay with doing a little algebra. Alright. Okay, let's move on to problem 2b. This is actually having us prove the sum of cubes from 1 cubed to n cubed is n squared times n plus 1 quantity squared over 4. The curious thing about this is that's the sum of the just the plain numbers 1 to n quantity squared, right? Our formula for the sum of the numbers from 1 to n is n times n plus 1 over 2. You square that, you get this right here, which is pretty interesting, actually. Okay? So again, if we're going to prove this using induction, my proof would look a little something like this. I would say, okay, note that. It's going to look very similar. Note that 1 cubed is 1. And let me look at this formula. 1 squared times 1 plus 1 squared over 4. Well, that's 1, and this is 2 squared, so this is 4 over 4, which is also 1. So the initial step, or the basis step, holds. Okay? Now, we want to assume that this formula holds for k and then show that it must then work for k plus 1. So now assume that if we add up the cubes from 1 to k, that gives us k squared, k plus 1 squared over 4. And let's consider the sum with an additional term at the end, where we add the cubes up to k plus 1 cubed. Okay? So this sum, k plus 1, is this sum just to k, and then the k plus 1 term would be k plus 1 quantity cubed. Okay? Now we know a little bit about that first term, right? That's our assumption. So this would be k squared, this part right here, would be k squared, k plus 1 quantity squared over 4, and then plus k plus 1 cubed. Alright, now it's important to keep in mind what we want our answer to look like. So let me again scratch paper off to the side here. We'd want to replace this with k plus 1, so we'll end up with k plus 1 squared, and then k plus 1 plus 1, that's k plus 2 squared over 4. So some things are happening here that are encouraging. We've got a common factor of k plus 1 quantity squared. I've got the 4 in the denominator, so let's at least get our common factors out. That would leave me with k squared over 4, and then plus k plus 1. So common denominator here, I would think, k plus 1 squared, and then inside here, if I get a common denominator of 4, this is k squared, and then I'd have to say 4 times all of this business right here, so plus 4k plus 4. But this actually is a perfect square, right? This is k plus 2 quantity squared. So this is k plus 1 squared, quantity squared, and then this is k plus 2 quantity squared all over 4, which is what we were trying to find. Alright then, thus, the inductive step holds, and therefore formula holds by induction for all natural numbers n. Okay? This is a recurring theme with all the induction proofs. You know, we try to use the information that we found, right? Or that we've assumed, and then we kind of build on that and show that the next one has to happen. Alright, problem C says, okay, let's say we add up the squares in order, but we alternate the sign in front of them. So when I is 1, this would be 0, so it would be positive, and then negative, and then positive, and so on as we get bigger. Let's show that that equals this right here, which is kind of curious. This is kind of the sum of the i's in order, but the sign is going to change in front of it. Okay, And we want to show this for n equal 1, 2, 3, 4, 5, 6, and on. So the initial step here is with n equal to 1. So let's look at this with n equal to 1. I would have a minus 1 to the 1 minus 1 times 1 squared. Well, this is 1, the 0 exponent 1, and then 1 squared is 1, so this is just 1. And I normally say something like note that, just forgot to write it down. And if I look at this formula now, negative 1 to the 1 minus 1 times 1 plus 1 over 2 is, well, this is positive, this is 2 over 2, so this is 1. So the initial step holds. Okay? Now, we assume that this formula holds for some k. Oh, and the thing I've been leaving out of this, it can't just be any k. It's got to be a k bigger than, so I'll say it this time. It's kind of implied the last time, but let me say it. Assume that this formula holds I going from 1 to k, negative 1 I to the I minus 1, I square, and this will equal negative 1 to the k minus 1, k times k plus 1 over 2. And what I should have been saying all along is for integer k, right? That's very important, but I think it's kind of assumed because it's an index. But also that k is greater than or equal to our initial step number. So let's consider the sum now from 1 to k plus 1, negative I to the I minus 1, and I squared. Okay, so again, what we do is we write this out. We don't write it out, but we say, okay, take the formula up to the sum up to the kth term. Okay, and that's what we've made the assumption on. And then the last term would be, okay, we've got a negative 1 to the k plus 1 minus 1, that's here, and then we've got k plus 1 quantity squared. Now, by assumption, this part right here is this. Negative 1 to the k minus 1, k plus 1 over 2, and then we've got this term, the negative 1 to the k, just k, right, plus 1 minus 1, and then k plus 1 squared. Now, even though this looks messy, it's really not that bad. We need to kind of keep in mind what we hope the answer looks like. So let's think about that just a little bit. Here's my scratch work area. If we put a k plus 1 in this, we've got a negative 1 to the k plus 1 minus 1, so that's the k. And then I would have k plus 1 there and k plus 2 there all over 2. So that's what we're hoping this adds up to. So it makes sense that I would want to take out common factors of k plus 1 and also factor out a negative 1 to the k, because these are factors in our answer. So when I do that here, that's actually one more than I've got. So to get that negative 1 at the top that I need to pull out, I also need to have a negative 1 in the bottom, which makes the whole thing negative. So this is a negative k plus 1 over 2, and factoring this out here, I'm just left with a 1. Okay. I'm missing a sign somewhere here. Let me think about this. Okay. Oh, well, I know one thing I'm doing. I factored this out. Okay. Yeah, that makes a lot more sense, actually, now that I got that out. Okay. So this is... Yeah, all right, I'm good with it. I'm good with it. Yeah, and I'm just messing up. In fact, I messed that whole step up. I think my brain must be falling asleep. So let me just do it again. All right, negative 1. Let's do it right. To the k, and I guess honestly, to avoid having that negative in there, I could do it this way. Let's just take out for the moment the k minus 1. Okay. And then I've got this other factor of k plus 1 I can pull out. And then what am I left with? So I'm left with here k over 2. I'm sorry, I think my brain fell asleep in the middle of that one. I'm getting a little late here. And then if I factor this out, I'm left with 1 negative there. Factor this out, I'm left with 1 k plus 1 there. Alright, so I'm sorry for that mess I made. Negative 1 to the k minus 1, k plus 1. And now we would want to get a common denominator here, I think, 2. So k, and I'd have to say 2 times all this, so a negative 2k, negative 2. Alright, so negative 1 to k minus 1, k plus 1. And then this is going to give me a negative k minus 2 over 2. So I've got a negative in each of those terms I can pull out and bring it right here. So this is now negative 1 to the k, and then my fraction would be k plus 1, and I'm left with k plus 2 all over 2, which is what we were trying to show. I'm sorry, I knew something was wrong as soon as I wrote that down. Okay. So, the induction step holds, and therefore by induction the formula holds for all n that are natural numbers. Sorry, not the neatest proof. Yeah, that is one of the advantages of the iPad. I could always go back and erase messes like that, and doing it in ink, just get what I get. So I'll try not to make another mistake like that. Okay, so let's do problem D. And this is where we're adding up actually odd numbers. If you think about this, when I is 1, this is 2 minus 1, 1. When I is 2, this is 4 minus 1, 3. So we're adding up the first n odd, positive odd numbers. And when you do that, you get n squared. It's kind of a neat idea. Now, I will say this before we go about proving it with induction. You know, they've asked us to use induction to prove these things. This is one we could prove directly. We have a formula for the sum of I from 1 to n. And we can handle the 2, pull it out in front. We can add up n ones and get n. So we don't have to necessarily do this with induction, but let's do. The first case that we're going to look at is when n is 1. So my proof would start with something, probably start at that point. Note that. And so when I is 1, this is 2 times 1 minus 1, just plugging in here, which is 2 minus 1, 1. And if I look at this side of it, 1 squared is 1. So the initial step holds. Now, let's say if we take the first k odd numbers, 1 to k, that gives me k squared. For, this is very important, integer k greater than or equal to 1. Okay. And now let's consider what happens if we add up the first k plus 1 odd numbers, 2i minus 1. Now I can't say it's equal to the formula, right? I have to figure that part out. But what I would do is I would take the first k odd numbers, which we have an assumption on, and then add in the k plus 1 odd number, which would be 2 k plus 1 minus 1. Okay? Now it's pretty obvious what we want this to look like, k plus 1 quantity squared. These first k terms, we're assuming that that is actually k squared. Okay? And then this is 2k plus 2 minus 1. So k squared plus 2k, and this is plus 1, and we're in business because that is a perfect square. That's k plus 1 quantity squared. So thus, the inductive step holds. Therefore, by induction, the formula holds for all natural number n. Okay? There we go. Okay, that wasn't very hard to prove. Now we could have, like I said, we could have proved that directly. Okay? But it was a good demonstration of how we would do an inductive proof. Okay. Part E of problem 2 asks us to prove that if we take the sum of the squares of the first n odd numbers, that we get this formula right here. And again, this is one using our results from Part A and our knowledge of adding up, 1 through n. We could multiply this out, get the I squared terms, the I terms, the constant terms, and derive this directly based on our other information. But it may actually be easier to do this through induction. So our first case is when n is equal to 1, so my proof would look something like this. Note that. And if I add up the first one, I get 2 times 1 minus 1 quantity squared. This is 2 minus 1, 1 squared, which is 1. And if I look at the formula, this is 1 times 2 minus 1 times 2 plus 1 over 3. So this is 1, that's 3 over 3. 1. So the initial step holds. Now, let's let this formula hold for some k bigger than 1. One is your k greater than or equal to 1. And consider what happens if we add the squares of the first k plus 1 terms. Okay, well, we can certainly add it to the first k. And we've made an assumption about what that is. And then the last term here would be what would happen if we plugged in k plus 1 minus 1. And this is quantity squared. So by our assumption, this would be k and then 2k minus 1 and then 2k plus 1 over 3 plus, and this would be 2k plus 2 minus 1. So 2k plus 1 squared. Okay. Now, we might want to take just a moment and think about what this should look like when we're done. I should have a k plus 1 factor. If I put k plus 1 here, I get 2k plus 2 minus 1, so that is 2k plus 1. And then 2k plus 2 plus 1 is 2k plus 3, all of that over 3. So the 2k plus 1 common factor is encouraging. We can get a common denominator of 3 here in a few minutes. Let me go ahead and get this 1 factor of 2k plus 1 out of here. And so that leaves me with k times 2k minus 1 over 3, and then plus just 1 factor of 2k plus 1. So a couple things need to happen. We need to multiply out that numerator. We need to get a common denominator of 3. K squared minus k, and then plus, if we're getting a common denominator of 3, I have to multiply this by 3. So plus 6k plus 3. Alright. So still holding on to my 2k plus 1 here. And what do I end up with here? 2k squared plus 5k plus 3. So it looks like to get the 5, I want 2 times 1 and 3 times 1 added together to get the 5k. So it looks like here this would be 2k plus 3 and then k plus 1 all over 3. And if you'll notice, that's exactly what we're trying to get, right? So thus the inductive step holds. Therefore, by induction, the formula holds for natural number n. Okay. So again, it's good to have your algebra skills honed up and sharp and ready to go on these. Okay. Kind of continuing the theme, the next problem has us adding up the first n odd numbers cubed, each one cubed. So let's do that one. This kind of parallels what we did with I. We did I kind of in class, then I squared, then I cubed, added up. We're again doing this for natural number n, so the first part of my proof would be with n equal to 1. If I take 2 times 1 minus 1 and cube it, this is 1 cubed, which is 1. I probably would say something like, note that. And look at the formula, 1 squared, and then 2 times 1 squared minus 1. Let's see, this is 1, so 2, this is just going to be 1. So, the initial step holds. Okay. And now we want to look and assume the formula holds for the first k odd numbers being cubed and added together. To k, 2i minus 1 quantity cubed is k squared, 2k squared minus 1. Okay. And for integer k greater than or equal to 1, and consider by going 1 to k plus 1, again we want to build on our assumption, so let's take this up to k. And then the next term, if I plug a k plus 1 in this, I get 2k plus 2 minus 1. So this is 2k plus 1 quantity cubed. Okay. And so now using my assumption, this is k squared, this part right here is k squared times 2k squared minus 1, okay, plus 2k plus 1 cubed. Now I'll tell you, this one's a little ugly because there's not a great common factor that you can easily pull out of this, okay, as a common factor. We've done that in the past. It worked really nicely. What we'd like to end up with here, it's pretty clear, would be k plus 1 squared, and then 2 times the quantity k plus 1 squared minus 1. We're going to have to work at this a little bit, so let's just go ahead and clean this up best we can. I don't have a good common factor that I spot there, so all I know to do is just multiply things out. This would be 2k to the 4th minus k squared. It's right here. And then this would be 2k cubed, and then 3 times 2k squared times 1 plus 3 times 2k times 1 squared, and then plus 1 cubed. So what does that get us? 2k to the 4th. I've got here actually 8k to the cubed, And then let's see, this would be 4k squared times 3, that's 12k squared minus 1. So that's plus 11k squared. And then a k term right here, this would be 6k, so plus 6k, and then plus 1. Okay. Kind of an ugly creature, but when we look at what we're hoping to pull out, we should have a couple of factors of k plus 1 that would come out. And the way to check that is with synthetic division. You know, the factor would be a negative 1. It's k plus 1, but the thing that makes that 0 is a negative 1. And then list your coefficients here. Hopefully you kind of remember how to do this from your old algebra days. So bring down your 2. 2 times a negative 1 is a negative 2. This is 6. 6 times a negative 1 is a negative 6. This is a 5. 5 times a negative 1 is a negative 5. This is a 1. And then 1 times a negative 1 is a negative 1. You get a 0. And so this then is equal to k plus 1 times, and you lower the degree. This is now 2k cubed plus 6k squared plus 5k plus 1. And hopefully I can do this again with k plus 1. So let me try that one more time. Let me say, okay, negative 1 is the 0 there. Bring down the 2. 2 times that's a negative 2. Add 4. 4 times this is a negative 4. Add, get 1. 1 times a negative 1 is negative 1. You get a 0 remainder. And so this is now, I've got a second k to the k plus 1 that I can pull out of there. And now that leaves me with 2k squared plus 4k plus 1. Now, really, I want to make sure that my answer has this minus 1 in here. Okay? So when I do this, I think the way I would try to write this is plus 1 minus 1, which would give me plus, you add 1 in, but then you subtract 1 out. Okay, so there's my minus 1. Here's my factor of 2. K squared plus 2k plus 1. And that is a perfect square, so we're in business. K plus 1 squared. This is 2 times k plus 1 squared, and then minus the 1, which is what we were trying to get. So thus, the inductive step holds, and therefore, by induction, the formula holds for natural number n. Okay? The last problem in that set is an inequality, and this is where things get a little touchy. Inequalities give you a lot more freedom, but they also, that freedom can be debilitating because you don't know exactly what to do. So let's take a look at this one last problem, which is an induction proof where we have to prove an inequality instead of an equation. Okay, we want this to hold for integer n 2 or greater. So that's where we would start our induction proof. Is note that, and so we want n to be 2. That means we've got 3 terms actually. We've got 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial. Okay, when you get this, this is 1 over 1, which is 1. This is 1 over 1, which is 1. And this is 1, 2 factorial is 2. So this is 1/2. So this is 2.5. And if I look at the formula, 3 minus 2 over 2 plus 1 factorial, well, 3 factorial is 1 times 2 times 3, so that's a 6. The 2's are going to cancel. So this is 3 minus 2 over 6. So this is 3 minus a third, or 2 2/3, which I should point out is greater than 2.5. So, sorry, my paper's getting crooked here. So the initial step holds. Now let's say it holds for some k that's 2 or bigger, integer 2 or bigger. Add up from 0 to k, 1 over those factorials. This is less than 3 minus 2 over, and this would be k plus 1 factorial. Now, for integer k, k being 2 or bigger. And let's consider what happens when I add up those terms, but I do the first, well, it's not the k plus 1 terms, but I add the next term in there. So I go in 0 to k plus 1, 1 over I factorial. And then again, what I want to show is this formula with k plus 1 in it. So let me just kind of get off to the side here. I want this thing to be less than 3 over 2, I'm sorry, minus 2 over k plus 1 plus 1. So k plus 2 factorial. That's what I'm shooting for. Okay? Alright. So let's write this out. This would be, let's do just up to k, I going from 0 up to k of the 1 over I factorial terms. And then the k plus 1 term here would be 1 over, and I plug in k plus 1 for I, and that's a factorial. So we use our assumption. This part right here is less than, strictly less than, this, 3 minus 2 over k plus 1 factorial. And then I've still got this term, the 1 over k plus 1 factorial. Okay? Now, we've got some terms there we can combine. Wouldn't hurt to go ahead and do that. This part would be 3, and then you got a negative 2 of these plus 1, so minus 1 over k plus 1 factorial. Now, the problem is this doesn't match what we're looking for, right? What we need here is a 2 in the numerator instead of a 1. Okay? The problem is if I just, and I got to have k plus 2 in the denominator instead of k plus 1, k plus 2 factorial instead of k plus 1 factorial. So, to get the denominator looking like this, I could, and notice if I'm doing a step that's strictly equal, I just put equals. If there's a step that's strictly less than, I put that in. Okay. But what I can do to get this is multiply by k plus 2 in the top and the bottom. So 3 minus, and I've got k plus 2, and then this would be k plus 2 factorial, because I've got everything below that in there already. Okay. Now, this is where, when you think about this k, okay, what I'd like to do is just say, well, can I just drop the k plus? Okay. Well, I think that you can. Let's think about this just a little bit. The k plus 2, as it is bigger than 2, right? And I'm subtracting. Now that inequality is kind of going the wrong way, but if I'm subtracting, then that would be strictly less than just having a k, just having a negative 2 up there. So that's makes it actually legal for me to then say, oh, okay, well, that's strictly less than if I just put a 2 up there over my k plus 2 factorial. Okay, does that make sense? With k being 2 and bigger, it's definitely bigger than 2, and so subtracting it would be less than a negative 2, and they have the same denominator, so that's the only difference. Okay. This is the inductive step, so the inductive step holds. Therefore, the inequality holds by induction. All right. Again, the thing to keep in mind, because you have so much flexibility there, is what's our goal? What are we shooting for here? What are we trying to get? Okay? And let that kind of guide you then into what you throw away and what you keep in those inequalities. Okay? All right, that's probably enough for this time. We'll pick up next time with problem 3 and have fun. Let's see. Oh, I know what I'm trying to do. Sorry. I think the more of this I do, the better I'll get at it. Let's take this out of full screen and stop. All right, I'll see you.